Welcome, curious minds, to another profound journey on the deep dive.
Hello.
Today, we're plunging into, well, a truly mind-bending stack of sources. They challenge our very understanding of what reality is made of, right down to its most fundamental stitches. Imagine if the core fabric of existence, everything from, say, the smallest, most abstract point in mathematics, to the powerful, mysterious force of gravity itself, held a paradox. A paradox so deep that only a blend of rigorous philosophical inquiry and cutting-edge physics could even begin to unravel it.
And interestingly, what if an ancient parable offered a profound, maybe unexpected light on these very mysteries?
Exactly. It's a journey that connects seemingly disparate realms of knowledge, doesn't it? It really shows the remarkable unity and interconnectedness of ideas when you look at them through a specific, insightful lens.
We're about to see how some radical thinking can bridge gaps we often just assume are uncrossable. It's quite fascinating, actually.
Absolutely. So our mission today is to extract the most compelling insights from two groundbreaking papers by Karim Daghbouche. First, the Heuristic Principle of Inability, which was published in Journal Academica, Volume 2, Issue 1, back on May 6, 2012.
And his subsequent paper, The Symmetry of Matter and Antimatter, from the same journal, Volume 2, Issue 3, published September 29th, 2012.
Right, and we're also drawing from a deeply symbolic and ancient verse, Surah 24.35 from the Quran. It offers a surprising lens through which to view these modern scientific and philosophical conundrums.
So we're going to explore what it truly means when our most rigorous formal systems, our mathematical models, our physical laws, hit an inherent limit, an inability to fully describe or define certain fundamental concepts.
And we'll see how this failure, quote unquote, might actually redefine the very concept of singular existence.
Yeah, and from there, we'll leap into the mind-boggling implications for some of the most profound mysteries in physics. Why matter exists at all, why we don't see equal amounts of antimatter, and the enduring enigma of gravity.
And as we connect these abstract ideas to that richly symbolic parable of light, get ready for some serious aha moments. These might just reframe how you think about reality itself. Okay, let's unpack this truly unique deep dive. Okay, so let's kick things off with a concept that might initially sound a bit counterintuitive, maybe even negative, but actually holds immense power. Karim Daghbouche's Heuristic Principle of Inability. In his paper from Journal Academica, Daghbouche proposes this as a really revolutionary way to approach and understand fundamental problems, whether they're in mathematics, physics, or even philosophy.
Right. The core idea is this. When a formal system, and you can think of it as a logical framework, like the rules of arithmetic or maybe the laws of electromagnetism, encounters a persistent, unresolvable limit, a true inability to explain or define something within its own domain.
Yeah.
This very failure isn't a dead end. In fact, Daghbouche argues this inability can pave the way for entirely new solutions, new knowledge, and even new foundational axioms that reshape our understanding. The problem, in a sense, gets redefined by its solution.
That's fascinating. So the limitation itself becomes productive.
Precisely. And what's truly compelling about this principle is that it isn't just some abstract philosophical idea floating out there. History is absolutely rich with examples that demonstrate its profound heuristic power. I mean, its ability to guide discovery.
Okay, like what? Give us an example.
Well, consider the age-old human obsession with the perpetuum mobile, the idea of a machine that could run forever, producing energy without any external input.
Right, the free energy machine. People have chased that for centuries.
Exactly. For centuries, brilliant minds and countless inventors poured their efforts into trying to build one. Yet their repeated, consistent failures, their absolute inability to achieve perpetual motion, didn't just lead to frustration. It fundamentally transformed our understanding of energy.
So the very impossibility of creating something led to the discovery of a universal law. That's a powerful inversion of how we usually think about progress, isn't it?
It really is.
Yeah.
These persistent failures, or what some physicists like Sir Edmund Whittaker actually termed postulates of impotence, they eventually led to the formalization of one of the most bedrock principles of physics, the law of conservation of energy.
Ah, okay.
Both Max Born in 1962 and Whittaker himself back in 1949 highlighted how these repeated inabilities transformed into foundational principles. We couldn't build a perpetual motion machine because energy is conserved. The inability redefined the problem and gave birth to a solution, or rather an understanding, far grander than just building a specific machine.
And it's not just about conservation, right? I think you mentioned it applies to things that are irreversible too.
Precisely. Take the second law of thermodynamics, for instance. It emerged from another fundamental inability, the impossibility of transforming thermal energy into useful work without some unavoidable loss, or without something getting hotter or colder in the process.
You can't break even, basically.
You can't even break even, thermodynamically speaking. Unlike the first law, which states a conservation of energy, the second law declares an inherent irreversibility. It defines the concept of entropy, a measure of disorder, you could say. It's a fundamental limit, a boundary, that became a universal principle governing all energy transformations. The inability to get perfect efficiency became the bedrock for understanding heat flow.
Wow. Okay, so conservation of energy, thermodynamics, and this pattern, this principle of inability, even extends to some of the biggest revolutions in physics, like Einstein's theory of relativity. How does that fit in?
But it fits in beautifully. Before Einstein, physicists were pretty much convinced that light traveled through a universal medium called the luminiferous ether.
Right, the stuff space was supposedly made of.
Exactly. They conducted extensive empirical efforts, most famously the Michelson-Morley experiment in 1887, trying to detect this ether, trying to measure Earth's motion through it. But all efforts failed. Persistently and undeniably failed.
They just couldn't find it.
They couldn't find it. And it was this absolute inability to observe the ether that prompted, well, a stroke of genius from Einstein in 1905. He didn't try harder to find the ether. He declared its non-detectability a principle.
So instead of endlessly searching for something that wasn't there, he flipped it. He declared its absence a fundamental truth about how things work.
Precisely. By assuming that the speed of light is constant for all observers, regardless of their motion, an axiom born directly from an inability to detect the ether, Einstein had to fundamentally amend the very concept of simultaneousness. Things happening at the same time became relative.
Which is completely counterintuitive to our daily experience.
Totally. And this radically revised Newtonian mechanics, leading to a profound interdependency of space, time, matter, energy, and electromagnetism. The original problem of the ether wasn't solved by finding it. It was redefined by Einstein's revolutionary new view of physical dynamics, where the speed of light itself became the ultimate constant, the ultimate speed limit.
That's truly mind-bending. The non-existence, or rather the inability to detect something, ends up redefining everything we thought we knew about space and time. And then in quantum mechanics, we have Heisenberg's uncertainty principle. How does that exemplify this inability principle?
Indeed. Before 1927, it was generally assumed in physics that physical values, like a particle's exact location and its exact momentum, could, in theory, be measured with infinite precision simultaneously. The better your tools, the closer you could get to knowing both perfectly.
Like measuring a car's speed and position seems straightforward.
For cars, yes, but not for quantum particles. Heisenberg's uncertainty principle revealed a fundamental limit. These quantities, like position and momentum, cannot be simultaneously known with arbitrary precision. There's an inherent fuzziness, a built-in minimum uncertainty, where their combined precision always remains below a certain fundamental value, Planck's constant.
So it's not just a limitation of our instruments, but a fundamental feature of reality itself. We can't know both perfectly, ever.
Exactly, it's baked into the cake. And setting this inherent conjugation, this linked uncertainty, as a principle, didn't just limit our ability to deterministically predict everything, like Laplace's demon might have hoped. It actually expanded physics into the strange and wonderful mechanics of atomic and subatomic scales.
How did limiting knowledge expand it?
Because by accepting this inability to perfectly measure both properties, physicists gained an entirely new, incredibly powerful framework for understanding the quantum world. It opened the door to wave-particle duality, quantum states, probability waves, broadening the field of application and the associated knowledge exponentially. The limit became the key.
Okay, so the core epistemological framework here seems to follow this clear, almost paradoxical pattern. First, there's a fundamental inability for an existing axiom or a set of axioms to adequately cope with or describe certain phenomena. Second, this very inability is then elevated, formalized, you might say, as a new foundational principle or axiom.
Right.
And third, and this seems the most crucial part, this new axiom then redefines the original problem where the inability first appeared. It transforms it into a solvable, or at least a newly understood, concept.
That's a great summary. It's like discovering the inherent limits of your map, allows you to draw a completely new, more accurate one, rather than just trying to force the old map to fit where it clearly doesn't.
Now let's take this powerful heuristic principle of inability and dive into what seems like the most abstract and fundamental concepts imaginable: the nature of a single mathematical point, or maybe even the number one itself.
Right, getting really fundamental here.
Daghbouche, in his paper on the principle of inability, leans into that ancient Pythagorean statement, everything is number, and applies this idea to the mathematical linear continuum. Essentially, he substitutes our concept of reality with this continuum, this infinite line of numbers.
It allows for a deep focus on abstract processes of projection, where any object we perceive or conceive of is ultimately mapped to numbers or points on this line.
Okay. And the core challenge then becomes, can we truly formally define a single point? Or the number one, can we isolate one in a way that makes complete logical sense within our mathematical systems?
And this challenge, bridging discrete points or numbers to a continuous line, it's not new at all. It's described as a central problem of the foundations of mathematics by thinkers like Frankel, Bar-Hillel, and Levy, way back. It traces its roots all the way back to the Eleatic philosophers in ancient Greece.
Venus paradoxes and all that.
Exactly. Grappling with paradoxes of motion and infinite divisibility. Can you ever really cross a room if you have to cross infinite halfway points?
Right. And this brings us to the work of mathematicians like Weierstrass, Dedekind, and especially Cantor in the late 19th, early 20th century. The Weierstrass-Dedekind-Cantor program.
Modern mathematical analysis, really spearheaded by Carl Weierstrass, aimed to arithmetize it, essentially, to build all of mathematics purely from numbers and their relationships, removing any reliance on shaky geometric intuitions about lines and points.
Get rid of pictures, stick to the numbers.
Pretty much. But it was Georg Cantor who truly revolutionized this by viewing the continuum, like that continuous line, as infinite sets of points. He laid the foundation for transfinite numbers, which allowed us to talk about different sizes of infinity. Some infinities are bigger than others.
Which is already a mind-bending idea.
Absolutely. Cantor's ambitious goal was to define real numbers, including all those numbers like pi or the square root of 2, the ones with infinite non-repeating decimals, without simply assuming they already existed on the line.
He wanted to build them.
Yes, using concepts like fundamental sequences and limits to essentially construct these irrational or real numbers from the more well-behaved rational numbers, the fractions. Dedekind's famous cuts and Cantor's well-defined limits became the symbols for these real numbers, forming a kind of enlargement of the rational numbers that filled in all the gaps on the number line.
So they were trying to build a perfectly solid, complete number line from the ground up, piece by piece, using only logic and numbers. But wasn't there a crucial assumption Cantor had to make? Something he couldn't quite prove.
There was, and it's a very important one. Cantor proposed an intuitive property as a foundational axiom. He stated that every single point on a line corresponds to a definite real number, and vice versa. One-to-one correspondence.
Seems obvious, right? A point is a number is a point.
It seems obvious to us now, maybe because we're so used to graphs and coordinate systems. But mathematically, it was an axiom, a starting assumption, not something he could rigorously prove from more basic principles. He essentially had to state, let's assume this fundamental connection exists to build his system.
Okay. And to really push the limits of what continuity and points meant, Cantor introduced these bizarre mathematical constructs, these perfect sets that are nowhere dense. The most famous example is the Cantor ternary set, or C3. Can you walk us through what this thing actually is and why it's so mind-bending?
Certainly. As defined by Cantor and reiterated by Daghbouche in his paper, the Cantor ternary set, C3, is constructed through an infinitely repeating process. Imagine you start with a simple line segment, say from 0 to 1, nice and continuous. Now, you divide this segment into 3 equal parts, and you remove the open middle third. So you take out everything strictly between 13 and 23, but leave the endpoints 13 and 23.
Okay, so now you have 2 smaller segments, 0, 13, and 23, 1.
Exactly. Then you take those 2 remaining segments, and you repeat the process for each of them. Remove their middle thirds, now you have 4 segments.
And you just keep doing that forever.
Forever. Infinitely. You're constantly removing parts of the line, leaving behind an increasingly fragmented collection of points, like dust.
Okay. What's left? What are the properties of this Cantor dust?
Well, the properties of C3 are genuinely astonishing and paradoxical from an intuitive standpoint. First, it's non-denumerable. That's a fancy way of saying it has the cardinality of the continuum.
Meaning?
Meaning it has as many points as the entire original real number line, from 0 to 1. even though we've removed infinitely many
Wait,
segments.
what? How can it have as many points if you've taken most of the line away?
That's the paradox. It contains as many points as the interval 0, 1, yet it contains no intervals itself, no continuous stretches of line whatsoever. It also has zero length in the conventional sense. If you add up the lengths of all the removed segments, their total length is exactly 1, meaning what's left has zero measure.
So it's infinitely many points packed together in a way that takes up no space and has no length, but still has the infinite size of the original line.
You got it. It's also compact and nowhere dense, meaning no matter how small an interval you pick on the original line, you'll always find gaps, points not in the set. Its Hausdorff dimension, which is a way to measure the fractal dimension, isn't 0 like a point or 1 like a line, but it's log 2 log 3, which is about 0.63.
So it's an infinite collection of points completely disconnected from each other, zero length, yet somehow collectively it has the size, the cardinality of the entire number line. That sounds like a mathematical paradox right there. It defies all intuition about space and points.
It absolutely does from an intuitive geometric perspective. Daghbouche then generalizes this concept to strength, where the length of the removed middle interval can vary depending on a parameter k.
Okay.
As this parameter k approaches infinity, the Hausdorff dimension of this generalized Cantor set, strength, actually tends towards 0.
So it becomes even more point-like.
Exactly. It creates a set that, in a purely mathematical sense, behaves like a point of an n-space without any topology whatsoever. Think of it as the most abstract, structuralist point imaginable.
Okay, here's where it gets really interesting and, frankly, profoundly challenging to my brain. Daghbouche makes a bold claim with his Proposition 1 that this SRIC, this single, non-dimensional, dimension 0, almost nothing point, still has the cardinality of the linear continuum.
Yes.
So how on earth can a single non-dimensional point, something with no perceived size or extension, contain as many elements, as many numbers, as the entire infinite real line? That's an astonishing paradox. It feels like it breaks math.
It feels like it breaks our intuition, certainly. It is a paradox if we cling to our everyday understanding of points in space. Daghbouche's proof, however, is mathematically sound. It involves a clever transformation. He maps the ternary expansion of Creek, which uses only the digits 0 and 2 to represent the points left in the set, to a binary expansion, using zeros and ones, by simply substituting the 2s with 1s.
Okay, a mathematical trick.
A very clever one. This transformation allows for the derivation of all points of the unit interval 0, 1, which is unequivocally known to have the cardinality of the continuum. So mathematically, the mapping works. The apparent paradox, where a single point contains an infinite multitude, arises because we are applying our conventional, intuitive understanding of space and physical distance to something purely abstract and mathematical.
So it's our assumptions about what a point should be or how numbers must relate to physical space that create this tension. It's like we're trying to fit an infinite amount of information into a box we assume is tiny and empty.
Precisely. Daghbouche argues that without any physical distance, without imposing our geometric intuitions, we can indeed occupy any imaginable number of points or arithmetic values within what we intuitively call a non-spatial entity, such as in a single point. It means that the point, at this abstract level, is not the simple dot we imagine. It's something far richer, far stranger.
And this purely mathematical abstraction has profound implications when we try to connect it back to the physical world, specifically mentioning the Planck length.
Yes, exactly. How so? What does a bizarre mathematical construct like Slake have to do with the smallest possible unit of length in the universe?
Well, the concept of a physically constructible Cantor set, one you could actually try to make by, say, cutting a wire infinitely, is challenged by the existence of the Planck length. It's the smallest theoretical length that has any physical meaning, though we can't directly observe anything that small. It's about 1.6 by 1035 meters, unimaginably tiny. This unit, as Daghbouche notes, is a direct consequence of quantum mechanics and measurement, inherently restricted by Heisenberg's uncertainty principle. You can't measure anything smaller. This demonstrates that physical space, the space we live in, requires a metric system, a way of measuring distance. It has a smallest possible scale.
Ah, okay.
So our abstract mathematical constructs, like SLEEK, which seem to have dimension 0 but infinite cardinality, highlight the potentially arbitrary nature of these physical conventions. They remind us that reality itself, at its most fundamental level, is not necessarily bound by our human-defined metrics of space and distance. It suggests that at these ultra-small scales, our ordinary notions of spatial extension can simply break down, and something more like the paradoxical Crick point might be closer to the truth.
So if a single non-dimensional point like Sleek can have the cardinality of the linear continuum literally contain as many elements as an entire infinite line, what does that imply about the very concept of the number one itself?
Right, the simplest number we have.
Daghbouche pushes this idea even further. He states in Proposition 2, along with Lemma 1 in his paper, that the number 1 has at least the cardinality of Church. And since Skrik has the cardinality of the continuum, this implies 1 is at least equal to any cardinality Cax.
Wait, 1 is equal to any cardinality, including infinite ones.
At least equal to, yes. This suggests that 1 must be redefined, not just as a simple singular unit, but in set theoretical terms, as simultaneously a single unit and a multitude. This is a truly radical reconception of something we take completely for granted.
It feels like saying the word apple somehow contains all possible apples that ever existed or could exist.
It's a similar level of abstraction, and it actually circles back to Cantor's own reflections on what a cardinal number really is.
Yeah.
Cantor described a cardinal number, a number that tells us the size of a set, like 1, 2, or even infinite sizes like Aleph null, as a result of a double abstraction.
Okay, what are the two abstractions?
First, you abstract away the specific nature of the elements in a set. Whether they are apples or oranges or numbers, it doesn't matter. Just that they are things, they become units.
Yeah.
Second, you abstract away their order. Apple orange is the same size as orange apple.
Right, the count is the same, regardless of what they are or how they're arranged.
Exactly. What remains after this double abstraction, Cantor said, is one, an intellectual image, a concept where all the individual elements become indistinguishable, all becoming one in terms of their count, their cardinality.
So 1 is already an abstraction, a container for things that we count as a single group. But Daghbouche seems to be saying it's a container for, well, potentially everything.
He takes it to the absolute limit. And this brings us to the ultimate abstraction in the paper, Proposition 3. This makes an almost unbelievable claim. Daghbouche refers to Cantor's own question about whether there is a system, let's call it tau, that contains all the transfinite cardinal numbers, all the different sizes of infinity, Aleph null, Aleph 1, Aleph 2, and so on. Is there a set of all infinities? And if so, is that set itself an Aleph, another size of infinity?
Okay, that's already making my head spin. What does Proposition 3 claim?
Proposition 3 states that this system of all Alephs, the totality of all infinities, is actually equal to 1. So 1...
Hold on. 1, which we perceive as finite, singular, the start of counting, is equal to the set containing all possible infinities. How can that possibly be consistent?
It's precisely this point where Daghbouche argues we encounter an unavoidable inconsistency at the very foundation of mathematics, or at least a paradox that pushes our logic to its breaking point. This implies that 1 is a consistent multitude embodying all infinities, yet it is simultaneously finite and represents absolute unity.
That sounds like a flat-out contradiction.
Within standard logic, it certainly appears that way. This is where Daghbouche argues we confront an ultimate inability of determination in the very language and formal systems we use to describe reality. As he highlights, referencing both Spinoza and Cantor, omnis determinatio est negatio.
Every determination is a negation.
Right. Every act of defining something, of saying what it is also an act of negation, of saying what it isn't. It's a limitation. When you define 1 as just a single unit, you negate its potential to be this infinite multitude.
So the more we try to pin down 1 or a point with our formal definitions, the more we realize the limitations and the inherent paradoxes within those definitions. It's like our language and math hit a fundamental wall where they just can't fully grasp what 1 truly is at its deepest level.
Exactly. And this leads us to Daghbouche's really profound proposal for what he calls an axiom of reality. Definition 10 in the paper. He cleverly inverts that Spinozan observation. If every determination is a negation, he suggests, then perhaps the reverse is also true. Omnis negatio est determinatio. Total negation, or the most undefined expression possible, actually yields something. Determination arises from non-determination.
Total negation yields something. How does he formalize that?
He represents this something with the Arabic numeral on, which signifies 1, but perhaps carries this deeper paradoxical meaning. And he defines this axiom as an equation. 0 UNEOA.
0 times infinity equals 1. Okay, that's definitely not an equation you'll solve in algebra class. It sounds much more like a philosophical or even mystical statement. What's the interpretation?
The interpretation is that from the ultimate undefinedness represented by 0U, nothingness interacting with totality, perhaps something, existence, 1, emerges. This axiom suggests that the most undefined state, the highest level of abstraction where our usual rules break down, actually yields existence itself.
Wow.
This something, Anna, is described as real, but not reality, maybe like a potentiality or a projection of a complementary notion. It encompasses multitudes and diversity as well as for unity simultaneously. It's a major intellectual leap that challenges our conventional binary logic, either, proposing instead that existence, or reality, might emerge from the fundamental paradox of unity and infinity coexisting.
It's a way of saying that the very deepest truths about reality might lie precisely in those places where our formal systems break down, where we face an inability of determination. The paradox isn't a flaw in the system, it is the system at some level.
That's a lot to wrap our heads around, isn't it? This idea that the most basic unit, one or a point, is paradoxically this infinite multitude.
It's wild to think how our fundamental understanding of something so simple is, well, apparently riddled with this kind of paradox at its core. But what if these deep philosophical inabilities we find in mathematics aren't just abstract curiosities? What if they echo fundamental challenges in the very real physical universe, like the enduring mystery of why matter exists at all?
Exactly. Let's take these mind-bending concepts, this idea of unity containing diversity, of stability emerging from paradox, and apply them to the physical world. Specifically, let's look at the persistent mystery of matter's very existence.
Okay, where do we start in physics?
We dive into the realm of particle physics, starting with Paul Dirac's famous 1928 equation. Now, this equation was a cornerstone of quantum field theory, the framework that describes particles and their interactions. It was truly groundbreaking because it formally predicted the existence of antimatter.
How did it do that?
Well, mathematically, it yielded solutions that described electrons, but it also yielded solutions with negative energy. These negative energy solutions were initially puzzling, but they turned out to describe particles with the same mass as the electron, but opposite charge, what we now call the positron, the electron's antiparticle. Equation 5 in Daghbouche's Symmetry of Matter and Antimatter paper shows this.
So it's a brilliant piece of mathematics predicting a whole new type of matter. But it came with a huge problem, didn't it? This is where it gets really interesting. If you took the equation at face value, it implied something disastrous.
Yes, disastrous is the right word. If left unaddressed, the existence of these negative energy states implied what physicists called a radiation catastrophe, which is illustrated in Figure 1 of the paper.
What's the catastrophe?
The catastrophic prediction was that electrons and atoms, which normally occupy positive energy states, could continuously fall into these lower negative energy states. And in doing so, they would release energy, specifically infinite amounts of radiation. This would make all matter fundamentally unstable, constantly collapsing and radiating away.
Which is obviously not what happens. Our desks aren't dissolving into radiation.
Clearly not. This was a massive theoretical dilemma. The math worked beautifully in many ways, but it predicted a universe fundamentally different from the stable one we inhabit.
So how did Dirac deal with this? He must have found a way around it.
He did. To circumvent this predicted instability, Dirac, in 1931, proposed an ingenious, if somewhat strange, semantic reference hypothesis. He suggested that the vacuum, which we intuitively think of as empty space, isn't empty at all.
Not empty. What's in it?
According to Dirac's hypothesis, it's entirely filled with an infinite sea of these negative energy particles, specifically negative energy anti-electrons, or positrons. All the positive energy states, the ones normal electrons occupy, are conversely empty slots above this sea.
Okay, that's a weird picture of empty space. So where do antiparticles come from then?
A hole in this Dirac sea, as depicted in Figure 2 of the paper, is then interpreted as a positive energy antiparticle. If an electron falls into a hole, it looks like an electron and positron annihilating. If energy creates a particle-antiparticle pair, it's like lifting an electron out of the sea, leaving a hole behind. This clever workaround allowed the energy and impulse operators in his equations to be rewritten, ensuring positive energy for observable particles and preventing that infinite annihilation cascade.
So it worked mathematically. It patched the problem.
It did patch the problem mathematically. However, it introduced this rather awkward concept of an infinite constant vacuum energy, the energy of this infinite sea of negative energy particles. Reconciling this infinite vacuum energy with observed reality, particularly with gravity and cosmology, has presented its own set of significant challenges for later physicists. It felt a bit like sweeping an infinite amount of dust under the rug.
So it was a brilliant theoretical move to save the mathematics from collapsing, but maybe it left some lingering questions about the true nature of empty space and this underlying sea. Now, in modern particle physics, we rely heavily on something called CPT symmetry, right? How does that fit in with this picture of matter and antimatter?
Yes, modern particle physics, which is built on the principles of Lorentz invariant quantum field theory, meaning the laws of physics look the same for all observers, regardless of their constant velocity, relies heavily on this fundamental symmetry called CPT.
What does CPT stand for?
Charge, parity, and time reversal. Parity is like looking in a mirror, spatial inversion. Charge is swapping positive and negative, and time is running the movie backward. CP symmetry essentially states that if you take any physical process, swap all the particles with their antiparticles, C, look at its mirror image, P, and run it backward in time, T, the resulting process should also be possible and obey the same physical laws.
Like a cosmic triple reflection.
Kind of. And this CPT symmetry fundamentally implies that particles and antiparticles are exact reflections of each other. They must have precisely the same mass, the same lifetime, if unstable, the same magnitude of magnetic moment, but exactly opposite charges and mirror image intrinsic spins.
Has this been tested?
Oh, yes. It's been empirically confirmed with incredible precision. For example, experiments at CERN comparing hydrogen atoms with antihydrogen atoms have shown them to have identical energy levels, exactly as CPT symmetry predicts.
Okay, so if they are such perfect mirrors of each other, identical in mass, created together, then we hit another colossal puzzle. Why does matter exist at all? This brings us to the baryon and lepton number problem.
Exactly. The standard model of particle physics, our best current description of fundamental particles and forces, suggests that any interactions that create particles always create particles and antiparticles in exact pairs. This process meticulously conserves certain quantum numbers, like baryon number, related to protons and neutrons, and lepton number, related to electrons and neutrinos. Daghbouche discusses this in Section 4 of his Symmetry of Matter and Antimatter paper, using thought experiments.
So for every particle created, an antiparticle is also created, like getting one heads and one tails every time you flip a coin.
Precisely. This means if the universe began with a net zero of these numbers, which seems the most natural starting point, essentially an equal potential for matter and antimatter, it should logically still have zero today. All the matter and antimatter created in the Big Bang should have found each other shortly afterward and annihilated completely, leaving behind only a universe filled with radiation like light.
But that's not what we see. We see galaxies, stars, planets, us, all made of matter. Where did all the antimatter go? Or why was there more matter to begin with?
It is indeed one of the grandest cosmic puzzles. Why the overwhelming asymmetry? Mainstream physics attempts to explain this by postulating that a tiny imbalance, a slight preference for matter over antimatter, occurred very early in the universe's history. This process is known as baryogenesis.
Creating baryons, creating matter.
Right. But the specific mechanisms required to create this initial imbalance remain highly speculative and, crucially, unproven. The famous physicist Andrei Sakharov, back in 1967, proposed 3 necessary conditions for baryogenesis to happen. You need processes that violate baryon number conservation, processes that violate both C and CP symmetry, meaning charge conjugation and combined charge parity symmetry aren't perfect, and the universe must have departed from thermal equilibrium.
Do we know of physics that meets these conditions?
We know of some CP violation in certain particle interactions, but not nearly enough to explain the observed matter dominance. And the physics required for baryon number violation and a strong departure from thermal equilibrium in the early universe is still largely unknown and theoretical. We haven't observed protons decaying, for example. Furthermore, attempts to postulate mechanisms where matter and antimatter were somehow spatially separated to prevent annihilation, like those proposed by Omnes in 1969, haven't been consistently established or observed either. The core mystery remains stubbornly unsolved within the standard framework. If particles and antiparticles are perfect mirrors, CPT symmetric, why are we here, living in a universe filled only with the matter half?
And this profound question about matter's existence leads us directly to another one of the most fundamental open questions in physics. A true enigma that has puzzled thinkers for centuries. Gravity itself.
Ah, yes. Gravity, the force we know best and perhaps understand least, fundamentally.
Why is it that all matter is universally attractive under gravity? That seems unique compared to the other fundamental forces, doesn't it?
It's profoundly different. Think about it. Electrostatics, magnetism, the whole realm of electromagnetism, they all exhibit both attractive and repulsive forces. Positive charges attract negative, but like charges repel. Magnetic north poles attract south poles, but north repels north, south repels south. There's a duality of balance.
Well, the gravity.
Gravity only attracts. It always pulls things together, never pushes them apart, at least as far as matter is concerned. Why this universal, unwavering attraction? Why no anti-gravity based on some property analogous to charge?
Current theories don't really explain that why, do they? They describe how it works, but not the fundamental reason for the attraction-only nature.
Not in a completely satisfying way, no. Furthermore, while Einstein's general relativity was a monumental achievement, elegantly explaining why inertial mass is equivalent to gravitational mass,
Meaning why the resistance an object has to being accelerated, its inertia, is precisely the same as its gravitational charge, its tendency to fall in a gravitational field.
it doesn't fully explain why all masses, regardless of their composition or internal structure, whether they're made of feathers or lead, hydrogen or uranium, fall with the exact same acceleration in a given gravitational field. Galileo supposedly dropping things off the Tower of Pisa.
The equivalence principle.
Yes. This fundamental observation, that the gravitational force per unit mass is identical for all matter, remains a deep mystery, not fully elucidated by our existing theories. Why this universal equivalence? It's not just that they fall, but why they all fall alike, perfectly, regardless of what they're made of.
It's like gravity has this incredibly democratic yet singularly focused nature. Always pulling the same way on everything per unit mass. It feels like a deep asymmetry built into the most pervasive force in the cosmos, contrasting sharply with the balanced push and pull we see elsewhere.
So with these colossal mysteries laid out, the potential instability of matter, radiation catastrophe, the missing antimatter, bearing asymmetry, and the uniquely attractive universal nature of gravity, Daghbouche brings us back full circle to the implications of Heisenberg's uncertainty principle, the principle we discussed earlier in the context of inability and fundamental limits.
Right, the idea that you can't perfectly know certain pairs of properties like position and momentum at the same time.
Exactly. And as Daghbouche notes in Section 6 of the Symmetry of Matter and Antimatter, this uncertainty principle imposes fundamental limits on how tightly you can localize a particle, how precisely you can pin down its position.
What happens if you try to pin it down too precisely?
Well, more specifically, any attempt to localize an elementary particle to a region smaller than its characteristic Compton wavelength, that's a specific tiny length scale related to its mass, requires pumping in a lot of energy. And if that energy exceeds twice the particle's rest mass energy, 2 LC2, something fascinating happens. You inevitably create particle-antiparticle pairs out of the vacuum.
So the very act of trying to squeeze it too tightly creates its opposite.
In essence, yes. The energy you use to localize it gets converted into new mass, following Eve's Marcia. What this implies for our understanding, Daghbouche argues, is that elementary particles effectively have no spatial localization, in the classical sense, below this specific Compton wavelength. They aren't little billiard balls with definite positions. They are inherently fuzzy, described probabilistically by wave functions.
So the fuzziness is fundamental, and trying to overcome it just creates more particles. This sounds like it sets the stage perfectly for Daghbouche's radical solution, doesn't it?
It absolutely does. This insight into the limits of localization leads directly to Daghbouche's single particle reference hypothesis, which he terms the biparticle hypothesis. It's presented in section 6.1 of the paper.
Okay, what is the biparticle hypothesis?
It proposes something quite revolutionary. It says that a particle and its corresponding antiparticle are, in essence, not two fundamentally separate entities just waiting to annihilate each other. Instead, they are intrinsically one fundamental entity, a biparticle, when that entity is localized above its Compton wavelength. In the stable lower energy state, the particle and antiparticle aspects exist together as a unified whole without interaction or annihilation.
Whoa, okay, pause there. So the electron and the positron aren't separate things that randomly meet and destroy each other. They are two aspects of a single, unified, stable entity, as long as you don't disturb it too much.
That's the core idea. It's only when this biparticle is localized below its Compton wavelength, meaning when it's subjected to high energies greater than or equal to 2 MeV2, that the conventional quantum field theory interactions we typically observe, including particle-antiparticle separation and potential annihilation, come into play.
So the default state is unified and stable.
Therefore, the central statement of this hypothesis is every particle above its Compton wavelength is a stable biparticle. Matter, as we normally encounter it, exists in this stable biparticle state.
This completely flips the script. The stability of matter isn't some cosmic coincidence or something requiring an ad hoc Dirac sea of negative energy particles filling the vacuum. It's an inherent property of this unified biparticle entity when it's in its calm, lower energy, less localized state.
Precisely. This hypothesis fundamentally shifts the existential constraint of stability to an ontological one, as Daghbouche puts it in section 6.2. Stability becomes a question of what the particle is, its ontology, rather than just how it manages to exist, its existential constraints within a potentially unstable framework.
In the notorious radiation catastrophe from Dirac's original equations?
It's resolved, or rather, it never arises in this picture. The biparticle is inherently stable in its ground state. It doesn't need to radiate energy because it's not in danger of falling into lower energy states. Its unified nature is the stable state at low energies.
So instead of trying to force matter stability into existing formalisms with patches or extra assumptions like baryogenesis, this hypothesis proposes stability is an inherent property of the fundamental constituents of matter at certain energy and localization scales. It feels like a much more elegant internal solution to the problem of why stuff sticks around.
It aims for that elegance, yes. It suggests the paradoxes arose from looking at particles and antiparticles as fundamentally separate entities from the outset, rather than as two facets of a single underlying reality.
Okay, this is huge. And this is where the biparticle hypothesis offers a truly fascinating new perspective on gravity and that long-standing open question of quantum gravity, as discussed in Section 7 of the paper. This could be the key to solving those gravity mysteries we talked about earlier, the universal attraction, the equivalence principle.
Exactly. Let's connect the dots. If all fundamental matter that we observe in the universe is, at its core, composed of these stable biparticles,
meaning everything is fundamentally made of these unified particle-antiparticle pairs.
and if each of these biparticles inherently contains both positive and negative aspects, both a matter and an antimatter component, bound together, then what would the nature of their interaction be?
If it contains both, maybe the opposing aspects naturally attract each other internally.
That's the proposal. Their inherent interaction, if they are not separated by high energy, is fundamentally attractive. This offers a radical, intrinsic explanation for why gravity is always attractive and never repulsive. The universal attraction of gravity isn't just mass attracting mass. It stems from the unified, internally balanced dual nature of these fundamental biparticles.
So the repulsion we see in electromagnetism is due to the separation of pure positive or pure negative charges. But at this deeper, unified biparticle level, the inherent state, the default setting before separation, is attraction. It's like an internal cohesion.
Precisely. And if this is true, does it also explain why all mass falls alike?
Yeah.
Why the equivalence principle holds so perfectly?
Let's think. If all observed matter fundamentally consists of these stable biparticles, and each of these biparticles, regardless of whether it forms a proton or an electron or something else, carries this unified positive and negative nature, then their inherent fundamental interaction, the thing that manifests as gravity, will always result in the same attractive force per unit of mass. Because the underlying entity responsible for the gravitational interaction, the biparticle itself, is the same fundamental structure for all types of matter.
Exactly. It's because the underlying gravitational charge, so to speak, isn't just mass, but this unified biparticle structure, which is universal. That structure inherently possesses this dual attractive nature when not forced to separate by energies exceeding the Compton threshold.
And Daghbouche also mentions that even if they are separated with energy but still close below the Compton wavelength, attraction is still observed, like in annihilation processes.
Yes, he argues that attraction is still the dominant interaction observed, for instance, in the processes leading to annihilation. This suggests a fundamental attractive interaction is woven into the very fabric of matter-antimatter duality within the biparticle itself, offering potentially powerful new insights to gravitational interaction.
This is truly profound. It reframes gravity not just as a property of mass-bending space-time, but as an expression of the fundamental attractive interaction within these unified matter-antimatter entities, a kind of internal harmony manifesting as a universal pull.
It seeks to provide a deeper quantum-level explanation for gravity's nature.
And it also provides a potentially elegant solution to the baryon asymmetry problem, doesn't it? Why we see only matter.
It does. In this view, matter appears to exist stably, dominating the universe, simply because it's just one aspect of this dynamically stable whole, the biparticle. It's not a lone survivor of an annihilation war that needed some mysterious imbalance to win.
So the universe isn't actually matter-dominated.
According to this hypothesis, no. It's biparticle dominated. And what we perceive as matter is just the stable, observable manifestation of these unified entities. It neatly sidesteps the need for speculative baryogenesis mechanisms by offering an ontological explanation based on the nature of being instead of a historical one based on an early universe event. The symmetry is still there, just hidden within the stable biparticle structure.
Wow. We've taken quite a journey already, from the abstract philosophical implications of inability in mathematics, revealing how one can paradoxically hold infinite multitudes, to the deep mysteries of matter, antimatter, and gravity in physics. And we've seen how this biparticle hypothesis, seemingly born from embracing those very inabilities in our current frameworks, offers a unique, maybe even elegant, solution to these long-standing paradoxes, explaining perhaps why matter exists and why gravity pulls everything together.
It's a compelling thread connecting these seemingly disparate fields.
Absolutely. And now we make another fascinating leap. We turn to an ancient source demonstrating how profound insights can emerge from truly unexpected places. Daghbouche's sources explicitly connect the symmetry of matter and antimatter and the nature of this unified biparticle, this light upon light, to a specific parable. The parable of light found in Surah 24, verse 35 of the Quran.
Yes, this verse, often called Ayat an-Nur, the verse of light, is one of the most famous, most discussed, and deeply symbolic passages in the entire Quran. It reads in the original classical Arabic.
Okay.
الله نور السماوات والأرض مثل نوره كمشكاة فيها مصباح المصباح في زجاجة الزجاجة كأنها كوكب دري يوقد من شجرة مباركة زيتونة لا شرقية ولا غربية يكاد زيتها يضيء ولو لم تمسسه نار نور على نور يهدي الله لنوره من يشاء ويضرب الله الأمثال للناس والله بكل شيء عليم.
And in English, using the phrasing adopted in our sources, which translates Allah as the God, to maintain consistency with the broader philosophical and scientific concepts being discussed, it reads, The God is the light of the heavens and the earth. His light is like a niche in which there is a lamp. The lamp is in a crystal. The crystal is like a shining star, lit from Suv, a blessed olive tree. Is located neither to the east nor the west, whose oil would almost glow even without being touched by fire. Light upon light. The God guides whoever he wills to his light. And the God sets forth parables for humanity. For the God has perfectest knowledge of all things.
Now, this surah is, at its heart, a profound parable. Traditional Islamic interpretations over centuries have often focused on the God's omnipresence, his divine guidance illuminating the path for believers, his universal knowledge that permeates and illuminates all things.
So light as a metaphor for truth, knowledge, guidance.
Exactly. It's generally understood that the God, by definition, cannot be pictured or confined by any physical form or image. And this light is a powerful metaphor for his absolute purity, his knowledge, his guidance, which illuminates the hearts and minds of believers and indeed the entire cosmos.
But the sources we're looking at today suggest a remarkably novel interpretation, one that resonates deeply with the very cutting-edge scientific and philosophical concepts we've just been exploring.
Yes, it posits that this ancient text, when viewed through the specific modern lens informed by the physics of symmetry and the philosophy of inability, offers surprisingly relevant insights into the fundamental nature of reality itself. It's quite a striking connection.
Okay, so let's break down this interpretation, looking at the verse through the lens of the physics we've been discussing. The verse starts, His light is like a niche in which there is a lamp. The lamp is in a crystal. The crystal is like a shining star. What's the significance of this layering? Light like a star from a lamp in a crystal.
This layering is key. It implies that the light we perceive, the light that shines brightly and allows us to see the world, the light that is like a shining star, is a brilliant, observable manifestation. But the verse clearly states that this brilliant manifestation isn't the ultimate source itself.
Ah, the source is deeper.
Yes, the true, fundamental source, the core of this light, is contained in a crystal, which houses the lamp. This structure parallels precisely the idea that what we observe in physics particles, matter, the phenomena of the universe, the shining star, might be brilliant manifestations of a deeper underlying, perhaps unseen reality.
Like the biparticle.
Exactly. Just as the lamp within the crystal is the more fundamental source than the light it emits, so too might observable particles, the star's light, be manifestations of a deeper unified reality, such as the biparticles, the lamp and the crystal. The shining star is the observed universe, but the crystal holds the unseen fundamental source of that light.
Okay, that's a fascinating parallel. And then there's the phrase, the crystal is in a niche. What does the niche suggest in this interpretation? It sounds like a location, but maybe not a precise one.
That subtlety is crucial here. The crystal containing the source isn't just out in the open, it's in a niche. This phrasing subtly echoes the Heisenberg uncertainty principle and the concept of non-spatial localization of fundamental particles that we discussed. It also resonates with the elusive, unpin-downable nature of the mathematical point, or one, derived from the principle of inability.
So the source itself can't be perfectly located.
Exactly. The ultimate source of light, like the fundamental point or the biparticle, cannot be precisely pinned down or localized in our conventional spatial terms. A niche suggests a place, maybe a containment, but not a definite singular point with coordinates. This connects directly to the quantum mechanical ideas of non-locality and perhaps even the zero extension aspect of fundamental reality, suggesting the very essence of existence might transcend our ordinary concepts of space and precise position.
Wow, okay. And then we get to the fuel for the lamp. Lit from the oil of a blessed olive tree whose oil would almost glow even without being touched by fire. This blessed olive oil is interpreted quite specifically as the stable biparticle itself. How does the oil's properties map onto the biparticle hypothesis?
This is perhaps the most direct and elegant connection highlighted in the sources. The oil's inherent stability, its blessed nature, and crucially, its potential to almost glow even without being touched by fire, without needing external combustion or energy input, is interpreted as resolving that major current paradox in physics we discussed, the radiation catastrophe.
The predicted instability of matter from Dirac's original equation.
Right. Dirac's equations predicted matter should collapse, constantly radiating energy away, needing fire just to exist, perhaps. But the biparticle hypothesis solves this by proposing inherent stability. The olive oil's natural luminescence without needing external combustion mirrors the biparticle's inherent stability above the Compton wavelength. It requires no external fire, no additional energy input to simply exist stably.
It glows from within. Its stability is intrinsic.
Its stability is intrinsic, just like the blessed oil that needs no external flame to emanate light. It's a beautiful metaphor for inherent stability, as opposed to a stability that has to be imposed, explained away, or propped up by external mechanisms like filling the vacuum with an infinite sea.
That's a really striking parallel. And what about the description of the olive tree itself, located neither to the east nor the west? What does that signify in this physical interpretation?
This phrase, describing the source tree's location, takes on a profound new meaning when applied to the biparticle and its interactions, particularly annihilation. When the biparticle, this unified matter-antimatter entity, potentially undergoes annihilation, especially at high energies or in very localized interactions below the Compton wavelength, the event itself might lack precise, conventional spatial localization.
So neither east nor west means everywhere and nowhere, not definable in ordinary space.
It suggests something like that, not definable within our ordinary spatial coordinates of east, west, north, south. This connects to the idea that during such fundamental processes, our usual concept of spatial extension might momentarily cease, or perhaps the process occurs beyond our familiar spatial coordinates altogether. It's consistent with the non-locality aspect of reality hinted at in the Heuristic Principle of Inability paper, and the general weirdness of quantum mechanics, where particles don't always have definite positions. It's a statement that the ultimate reality, especially in these high-energy transformations, transcends our simple spatial grids.
And finally, the exclamation, light upon light. How does that fit into this picture?
Nur ala nur, light upon light. This phrase powerfully reinforces the layered, multifaceted nature of reality suggested throughout the verse and echoed in the physics. It could hint at the cascading manifestations of fundamental existence from the ultimate, perhaps unknowable source, the lamp and the crystal in the niche, to its various expressions, the shining star, perhaps even hinting at the unity within diversity.
Like how the abstract mathematical one can encompass all infinities.
Or how the single biparticle contains both matter and antimatter aspects within its stable, unified structure. It speaks to a deep coherence, an underlying unity beneath the apparent multiplicity, a fundamental light generating further light. It's a profound statement about the deep interconnectedness and layered nature of existence.
What an incredible, truly mind-expanding journey we've taken today. I mean, really stretching the boundaries of how we think about things.
It certainly covers a lot of ground, from abstract math to particle physics to ancient scripture.
Absolutely. We started with the abstract philosophical implications of inability in mathematics, which rather beautifully, I thought, revealed how the very concept of one might paradoxically hold infinite multitudes.
Yeah, challenging our most basic numerical intuition.
Then we leaped into the profound, persistent mysteries of matter, antimatter, and gravity in the realm of physics. We explored how the biparticle hypothesis, which seems to grow out of embracing these very inabilities in our current frameworks, offers a unique, maybe even elegant solution to these long-standing paradoxes. It potentially explains why matter exists stably and why gravity is universally attractive.
Providing possible answers rooted in a different conception of fundamental reality.
And then, perhaps most surprisingly, how an ancient parable from the Quran, the verse of light, can be interpreted in a way that resonates deeply with these cutting-edge scientific and philosophical ideas, offering a remarkably rich, multi-layered understanding of reality that seems to bridge millennia and disciplines.
This deep dive truly highlights a core truth about how knowledge often advances, doesn't it? It progresses not just by diligently answering the questions we already have, but often by acknowledging the inherent limits of our current frameworks and our formal systems.
Right. Hitting the wall isn't failure, it's information.
Exactly. In doing so, we don't just hit a wall. Instead, we might open up entirely new avenues of thought and inquiry. The heuristic principle of inability, as Daghbouche frames it, shows us that sometimes admitting what we cannot determine or define with our existing tools, well, that leads us to redefine the very questions we're asking, and that pushes us towards profound new insights and a more complete, albeit maybe more complex, picture of reality.
So what does all of this mean for you listening right now and your understanding of what is real? It's a big question.
It is, and as Daghbouche's Heuristic Principle of Inability paper powerfully concludes, some questions, particularly ontological ones, questions about the fundamental nature of being, cannot be resolved with math or physics necessarily.
Our tools have limits when it comes to existence itself.
Precisely. Concepts as fundamental as one, or even the very idea that something exists, are, perhaps at their deepest level, fundamentally indefinable by our formal systems. They might require something more, like that proposed axiom of reality, the symbolic zero EO, an axiom that seems to transcend conventional logic and embrace paradox as fundamental.
So the final provocative thought for you to mull over is this. What if reality itself isn't something that fits neatly into our logical boxes? What if it is fundamentally, as Daghbouche suggests, a complementary notion where multiple, apparently contradictory properties yield something?
It challenges us, really, to contemplate existence and its fundamental nature beyond our current scientific and mathematical descriptions, to truly grapple with the idea that the deepest truths might lie precisely in those places where our systems seem to break down, where paradox isn't a flaw to be eliminated, but maybe the actual key, unlocking new dimensions of understanding.
It's a truly humbling and inspiring thought, isn't it? That the universe might be even stranger and perhaps more profoundly unified than we ever imagined. Hiding its deepest secrets, not necessarily in ever-increasing complexity, but maybe in a kind of simplicity that lies just beyond our current grasp, a simplicity built on paradox.
Food for thought, definitely.